So we're going to have another look at a question from the 2020 HSC Advanced Maths paper. So this is question 22. Question 22. Now, I've taught mathematics for quite a long time, a decade and a half, about 14, 15 years at this point, and I teach a lot of advanced maths students. A lot of kids in my cohort are usually in advanced maths, so about 10 or 20 advanced maths students a year. And I give them questions all the time. Over the course of the last 5 years, I've given this question to most of my advanced math students. Mostly they hate this question. They get it wrong and then they get annoyed. These types of questions are really interesting because it's not just about using a formula you've learned. It's about problem solving. You have to think, how is it that I can use my knowledge of all of the things I've gained in mathematics over the course of kindergarten up to year 12? How can I use that knowledge to get information that actually lets me find an answer? And this is very, very difficult to do if you're sort of just keeping up with learning formulas. So you will encounter questions like this in the exam. So we are given a regular decagon. So it's a 10-sided shape. And we're told the decagon has center 0. The perimeter of the decagon is 80. All right, so we'll write this down. Perimeter is 80 is centimetres, doesn't really matter what the unit is, but centimetres in this case. By considering triangle OAB, calculate the area of the 10-sided shape, give your answer in square centimetres, correct to 1 decimal place. So it tells us to consider triangle AOB. Right, when the question tells you to try something, that's probably going to be one of the easiest ways to do this. So we're going to draw a picture of this triangle, and there's half a dozen ways to use this triangle, right? You don't have to use one particular method. This is worth 4 marks, right? So a lot of the marks are for working, and using this triangle is going to be very helpful. So it's an isosceles triangle. This decagon is actually made up of 10 of these triangles. So there's one here, there's one next to it, there's one over here, and they go all the way around. Now, because they're centered at O, and because a circle revolution is 360 degrees, each one of these little angles down here must be 36 degrees. Right? Because there's 10 of them, they all combine to make up the circle. The angle around the point is 360 degrees, so that's 36 degrees. Because this is an isosceles triangle, these two angles, this one and this one, must be equal because they are the angles opposite the equal sides, so we know that they are equal. So we can actually calculate them because we know the angle sum of a triangle is 180. So this is alpha, 2 alpha, we'll call these alpha, plus 36, minus 36 from both sides. This gives us that 2 alpha is 144, divide both sides by 2. This tells us alpha is 72. So immediately we know both of these angles are 72. This is 72, this is 72. And so we have all the angles here. Now we were told in the question, I'm just going to move this over here. So this is for finding the angles. We were told the perimeter is 80, but we know that this is made of 10 of these triangles. And so this means that the top section of this triangle must be 8 centimetres because there are 10 lots of this in the outside of the decagon. So these all sum to make 80. So 80 divided by 10 gives you 8. So we know this length is 8. Now we just have to calculate the area of this triangle. If we multiply the area of this triangle by 10, that will give us the area of the decagon. Right? So that's all we're going to do here. We've used our knowledge of trigonometry and geometry to find information about this triangle. We found the information about the triangle, one length, all of the angles. Now we need to find its area. So I'm going to do this by cutting it in half. If I cut this in half, so it looks like this. This length is 4. This is 72. This is now 18. This is a right angle triangle. And I want to find its height, h. So I can use trigonometry to do this. I can use sine of 70. I can use tan of 72. Tan 72 is equal to h over 4. This implies h is 4 lots of tan 72. The area of this 1/2, the area here is 1/2 times 4 times the height. 1/2 times 4 times 4 tan 72. You could evaluate this at this point if you wanted to. I'm not going to, but you could put this in the calculator. We need to double this to get this triangle, or we need to multiply this by 20 to get the full decagon, because there were 10 triangles in it, which means there's 20 half triangles in it. So we can just multiply this by 20. So the area of the decagon is thus 20 times 1/2 times 4 times 4 times tan of 72. 20 times 1/2 is 10. 4 times 4 is 16. So this is 160 tan of 72. Now really from a higher maths perspective, this is the right answer, but the markers will want you to round this. So 160, and it says 1 decimal place. 160 times tan of 72 gives me 492.429. So area of the decagon is 492.429 ... So therefore the area of the decagon when rounded to 1 decimal place is 492.4 to 1 decimal place. And this is in centimetres squared. Right? It's in square units. In this case the units are centimetres. So this question is not really very hard if you use the right method to find values. This is one method. This uses right trig, which is quite nice. But you could have used non-right trig once you had angles in the triangle. You could have used geometry formulas from the beginning. You could have relied more heavily on geometry to try and find lengths and thus found areas. If you rounded through the question, you could end up with a slightly different answer at the end. So depending on how you round and how you do things in the question, your answers can be off by, +1, -1, something like that. If you are rounding as you're going through the question to lots of decimal places, then to 1 at the end, you will get the correct answer though. Right? And the markers would mostly prefer that you don't evaluate things until right at the end. They do in this paper, funnily enough. Their answer is actually not very good, the sample answer they provide, because they find a side length of this triangle. They find this and they evaluate this to 3 decimal places early in the question, then square it. So they compound error into their question they didn't have to have. But again, they don't really care, right? That if you have all of the stuff that gets you this answer and you have this answer, then it's correct, right? You will get all the marks. This is not hugely rigorous mathematics. This is just, use the maths you have to try and find a number that's pretty much the area. So the marker guidelines specify for us you have to find 8 to get 1 mark or equivalent. So you'll be starting to find either angles or sides in order to get the first mark. To get the second mark, they say find OA or equivalent merit. So in this case, this will be us finding the angles and then finding H. So we have to find H to get the second mark. To get the third mark, you have to calculate the area of the triangle or equivalent merit. So in this case, this will be us getting the 1/2 times 4 times 4 times tan 72. So the second mark was sort of this bit, the third mark was this bit, and then the fourth mark is getting the correct solution to 1 decimal place. And the marking can vary here, right? Depending on what you've done. The people that work in the marking center tend to be, they're NESA teachers, but they tend to be good NESA teachers, right? So they know if what you're doing makes sense or not, and they can correct their marking to adjust to your particular solution if you've done a particular type of solution, which also works, right? They're not going to look at the sample answers and comments they're provided and then mark. They're going to say, yeah, this kid understands that they're finding this value, they found it this other way, they got the exact correct solution. So there are a number of ways to do these, all of which, assuming you get the correct answer, are equally correct.